Hello. In the previous lecture, I discussed some interesting topics. That was alpha beta pruning, that is top of our theory that we discussed before. And Sprague theory, I defined what is direct sum of two games. Do I need to repeat to you what I discussed or not? Hello?
Hello.
Yes, please. Okay, we defined, if it's possible. Okay, I defined what is direct sum of two games. We have we can imagine it like we have two graphs, and in this graph we have two initial states, and we just we just choose in what of two these graphs we move. This is a direct sum of two games. Next, I proved some interesting, some useful properties. The most important is this definition. If you have two games, they are Grundy equivalent. If for any game C, the following is equality is satisfied. It means for any game, if we take direct sum of this, the result of the game will be the same. Okay, next I proved. Next, what is the most important? Okay. Here's the most important fact that I defined game on E stones like star E. Game on one nim stone, one nim pile like star E. And what? I proved that we have equivalence with that element of we have classes of equivalency and so on, and these classes doesn't intersect. Okay, then I proved the theorem that any game on Asaki graph is Grundy equivalent to some nim game on E stones. Do you understand what I told you, or what I have told you? So we have that any A game is Grundy equivalence to some game on some nim game on stones, and we found this E constructively. It means I gave function max g a1 and so on g a2 g a n that returns representative element of of class. Okay, do you understand me? Any game, any study, we know how to get representative element of class, and this element is just a star e game on e stones, name game on e stones. Do I need something repeat to you? Repeat something for you?
No, it's okay.
It's okay. Okay, what is max, by the way? I give example. We want to know what is representative element of this game. I remind you that game is pair of game and is pair of class and current state. Okay, and what is representative element of this game? We take max of this sets, and what is max? Max is minimum excluded. Means if we haven't four, this we get we that mean representative element of this game will be four. Will be a game on four stones. Okay, we have by the way, if you have some segment that begins from now, it means the max of this segment is max plus one. Okay. Okay. And I thought that I need to prove this fact because this fact is most useful for us. This fact is more useful for us. And do I need to repeat something for you now? No? Okay. Or no? Or no? Or yes? Okay, that's fine. I think. Um, where where do you text me? Общее. Where I don't see. I I heard some, but I don't see. Please write to this chat, to комната для учебы чат. This chat. And I will see what you text. Okay. To prove this theorem, we need to use the previous theorem. That is GA is equals to what? To this, да? Let's write this. Let's write it. GA is equal to this star E is game. Star E is name is name game on E stones. Game on E stones. We have only one stone. And here's E stones. And if we the first player and E greater than one, now it means we can win. We can always win. We take all the stones. But the games on E and G not equals to G, not equivalent, not Grundy equivalent. It's not is despite the fact that we can win on these games, just take all the stones. Okay, it's not Grundy equivalent. it's different classes. Different classes relative to Grundy equivalence. Okay, and we need to prove this fact that if we take one pile, 2 piles, we can find what it isomorphic, what it isomorphic relative to Grundy equivalence. Here we have 1 pile, here we have 2 piles. Okay, we use previous fact that we can define, for any A game, we can find what nim game is equivalent. Okay, use this fact and notice that GA is, if we take G E, it equals to E. Okay, it means if we take what, G E plus G, it equals to what? It equals to E plus G, and what? And we need to prove that this equals to G E plus G. Okay, and this is equals to what? According to our theorem, this is equals to max of what? Of all the games that we can move and max, and take max. We can go to E plus null game and so on, E plus G minus 1 game and so on. Так, star, and what? And we can take everything plus G and so on, and take E minus 1 star plus G. By the way, to prove this fact that that this equals to this, we already use that fact that we already use that fact that we know that так, 1 second, I forgot about mathematical induction. We suppose that we have already proved this fact for that this fact that just second, we have already proved this fact that for E plus G less than 1 second. I forgot. Let me look. We apply mathematical induction, but I forgot how can we apply it. Wait, let me. Sorry. Okay. In begin we just prove this theorem by mathematical induction. We say that e plus g equals to null. We make induction by e plus g and say that if e plus g equals to null, it means that that something that we have null stones, it obviously that null piles of two stones to two piles is two empty piles is equivalent to just null, just game on null piles. Okay, we consider that e plus g greater than null. We have already proved. We suppose that we have already proved that fact that if e plus g if we have numbers of stones and this number is less than e plus g, that means we have already proved that x plus y is equivalent to star x plus star y. Okay, we use that fact. We use this fact here. We use this fact e plus null. We want to take max of this. Okay, and we take it. Then okay, then we need to prove. That suppose e plus g belongs to f to what, to g. We defined it like f like max. We define the set like max of f and e g. We want to prove that this number not belongs to this set, and we haven't any number that less than and any number belongs to this set. It means if we prove this, it means max of these sets, this set will be equal to e plus g, because all the numbers less than e plus g, and we have segments of it. And we need to prove that if we take k that less than e plus g, this k belongs to this max, this set. Okay. 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 Suppose e plus g belongs to this set. So notice that it doesn't belong, because if we have like in this set we have we can get the sum if we this or this. And notice that k less than e here, k less than e here, and a less than g here. It means contradiction, because to get e, we this function is injective relative to k, and it means to get the sum we need that k that must be equals to g, or L must be, or k must be equals to e, or L must be equals to g. Okay, that means this number is not belongs to the set, doesn't belong to the set. Okay, next we need to prove that k, if we take k and e plus g and k less than e plus g, it means this k belongs to what? Belongs to this set. To this set. To f e g. We need to prove this. Okay, to use this fact. And we get that e plus g, that max of e plus g equals to e plus g. Okay, do you need something to repeat for you? For example, mathematical induction step, or what happens here, or what? It's better to what can I repeat for you? The induction. We suppose that we have already proved fact that if we have okay, mathematical induction base what? If we have two games, it equals to what? Null plus null. Okay, this fact is correct. Okay, this is base of induction. Okay, or not? Okay, this is base of induction, and we apply the induction here when we here. Okay. We have already proved for all this piles that we have this fact. We need to prove this fact, and I prove that e plus g, that e plus g is isomorphic to e star e plus star g. Okay, and to prove this, to prove this, I use this, that I need to take that if I take this interval, that all the numbers here, in max belongs to this interval. Wait, no, all the numbers of the set belongs to max. Okay, it means belongs to what f is g. It means if we take max of this, we get what? We get e plus g. Okay, because max is minimum excluded here. Okay, we get the same. Okay. Okay, and I need to prove that k, that if whatever we take a k, whatever less than e plus g, it belongs to this set. Okay, it means we have полуинтервал, как это, полуинтервал? Segment, not segment. What is this? This is half interval. Okay, half interval. Okay. So, what I need to do? Consider the sum. Consider the sum. Consider the sum. And what? This sum and denoted like not k, r. R and here r. And what? And notice that if we take r less than e plus g, that means we have that this number is describes like this, and we have just second, the first bit when we have difference, the first bit when we have difference, we just consider this bit like t, and it means if we take e less than e, since that fact that exists t less than e, we have c and e, and what? This is different t. I have already used t. We have to. How can we define it? P. Okay, P. We have P. Since we have P, that and we have that P plus what? P plus G belongs to F, because we build the set out like this. Okay, we build this set like this. We have here we have and so on E plus G. That means we can find this P less than E, and P plus E is belongs to G. Okay, it means we can take our E like P, it means R E plus E штрих E prime plus G what belongs to our set. Okay, I proved this fact. What it means? We take half interval now and plus G. We can find number whatever the number we took that less than E plus G. We can find it in our set, in our F E G. Yes, it means this half interval equals to what? To F E G. It means max of E F E G equals to max of now e plus g equals to e plus g. What we have proved? We have proved that that max of this set, where is it? We have proved that g of this, if this f is g, and if we take max of this set, we get e plus g. Okay? Or not okay? This is quite complex theorem. What I need to repeat for you? What I need to repeat for you? I can explain you everything. This theorem is really important because we can imagine, we can find вот, we can раскладывать, we can как divide our game into sets of piles. Okay, and we can find game is winnable or game is losable of what complexity? In complexity, all count of piles, because we just doing here. We just can store our piles and get the answer. If the answer is equals to null, it means game is losable. If it's more than null, it means game is winnable. Where is it? Fact. Where is it? Fact. If we have okay, if we have no piles, not stones a pile, it means we lose. Okay, if we have more than null pile, we win. We take all the spots. Do you understand me or not? This is really important theorem. Yes. Okay. And what can I repeat for you? Who who didn't understand me? Maybe it's mathematical dashing step. Maybe it's what happens in here. Here. Just we have G, and what is this one? For example, G is Grundy function. It's что? It returns us number of stones in давайте лучше я просто зачитаю, опять какую-то хрень скажу. Сейчас. Где я определил? Так. Вот. We denote once again we denote the game name with one pile of stones like star e, and Grundy function we denote like the number e such that a is isomorphic to star e. Grundy is isomorphic to star e as ga. It returns the number of stones in nim game. Okay, and according to this fact, g star e is equals to e. Okay, and we use this. And we use this here. Uh, okay, do you understand me? I can. Okay, if you have any questions, you can answer later in chat. In okay, please answer. Please ask questions in chat. So вдруг кто-то не понял. And I give my word to Fan. He prepared for us problems on Grundy Theorem.
Hello.
What? Fine, no.
Can you hear me?
Yes, I hear you. Did you prepare it?
Yeah,
Problems.
yeah. Okay. Let me share my screen from now, okay? Yeah, can I share my screen now? Okay, 1 minute, please.
Okay.
Um,
Do you want so I record you?
yeah, please, because
Okay. I
I'm
publicated
using
for to my channel. Okay.
okay.
I warning you.
Let me share my screen. So, mhm. Can you see? Can you see it? Can you see my screen now? Hello?
Yes, yes.
Okay. Yeah. So, let me first introduce the problem of the name schemes because I think it's better for you guys to understand this first, and we can start the problem about Sprague Grundy theorem later. So for yeah, just a moment. So I need to so yeah. So the first problem I want to tell you guys about is when we have uh, n pipe. So let's say we have one, two, three, four pies, big pies. We have let's say number of stones. Let's say we have 4 stones here. We have threes. We have two. Maybe here we have five, and here maybe we have ones. So the game is we try to uh, take stone from 8 pies, and you can take any number of stone that you want. But the last person to take their stone will be the winner. So if the game like from 2 person, I think Ramazan already told you about that. Is a combinatorial games or is there smaller version? Is a name game? So let's for examples here. I will draw examples. Uh, let's see. Mm, mm. So let's say if I have only 2 pies. Let's say if I have only 2 pies, I have I have 4 stones here, uh, and I have 1 stones here. So can anybody tell me how to play these games? Like if you are the first player and you need to win this game. So how you gonna play? You can take any number of stone that you want. Like you can take 1, 2, 3, 4, and from any pie that you want. You can take stone from this, or you can take stone from this. If anybody give, I mean, like your number of stone there, any number you think. Yeah, the first one, the first one. First player. You are the first. Or actually, it's not the. It's the introductory game. So you I will talk about the Sprague Grundy theorem later. So yeah, let me check the chat. No, not this one. You should take all of them, but leave one at least. You need to be the last one to take the stone to be the winner. So let's say, if you're telling me that you want to take all of this one, then the second player just take this one and he will be the winner, right? You want to be the winner if you need to take the last stone. So, uh, let's say for yeah, not yeah, you're making like you have the idea, but it's not you take all of them because yeah, that's right. If you take all of them, then the first player will lose because the second will take the stone. So yeah, you got the idea that you need to take some number of stones. So the second player will definitely lose, but it's not all the stone. It's not all. Uh yeah, so it's yeah, you guys got the idea, but it's not it's not be taking all of the stone. So let me tell you. So here we have four stone, and here you have one. So let's say if I take three stone from this, if I take three stone from this thing, so we only left like one, two, and we have two stone, right? Yeah. So if we take three stone from the first pipe, it is true. So how many stone? Ah, okay, because you just take that. You say that you take all the stone because we only take three. Okay. Uh. Okay. Sorry. Okay. My mistake. My mistake. Uh. mm, yeah. Yeah. Okay. Okay. So the why I introduced you the problem is because we know the how to solve it because but the algorithm for this problem that we need to sort the number of all the stone of the pipes. And if the result is positive, then this is a strategy for the first player to win. If the SOR results, the SOR are sums of the other pipe is zero, so you will definitely lose if the second player play optimally. So let's say, how can I? Yeah, let's give another example. Or yeah, so this is the first version of the game, but right now I want to introduce this another version where we need to apply the Grundy theorem. So we have the same. We have, let's say we have the same life. We have, let's say we have yes. But right now you cannot take any number of stone at you once, but you need to take let's say you need to take only from 1, 2, and 3. You cannot take let's say for the first example you can take like all the stone from the pipe, but now you can only take, for example, for this pipe you can only take like 3 stone from or 1 or 2 or 3, not 4. For the previous example you can take 4, but for not this example. So what are we gonna do here? What are we gonna do here? Can anybody like give me something about, because as Ramazan already told you guys about their grand uh s- Grundy theorems. So Just okay. Just let me add you something quick. So, what? Yeah, let me add you guys this. So, have ends ones, two, three, four, five, six. Can you calculate me for the Grundy numbers for each values here? I think we already know the calculate the Grundy values, right? Because our previous Ramazan just told you guys about that. So can anybody tell me what the Grundy value wants? I think you should write zeros here first because it's important. So um yes. Is are you guys following me? Like because can you guys hear me now? Yeah, okay, good. So for no, it's okay. It's okay. It's okay. It's okay. So for this problem, we are. I assume that you guys know that for this, for the Grundy theorem, we need to calculate the Grundy number for each bytes. We need to calculate Grundy number for each bytes for byte 1, 5 byte 2, for byte 3, and 5 byte 4. And we need to store all of them and to get the final value. And we will decide that the game is the first player can win or not. So how to calculate the Grundy number here? So let's say, or can anybody hear me? For the zeros, what the Grundy value is for this game? For this game, when you can only take one or two or three stones. Mm-hmm. It's okay. So yeah. So let me say about it. So if the game has zero stone, right? If zero stone, then how the game would be. The first player will be lose, right? The first player will immediately, right? So the Grundy value is zero. Grundy value is zeros here. And for example, if we have one stone, what the Grundy value is here? The first player can take the first stone and be the winner, right? And the next possible position of the game is zero. So the Grundy values here is Grundy values here is one, right? I need the same for 2 and 3 because we can take all the stone and be the winner. But what will be here? 4. For the Grundy value here for 4. Uh, yes, right. Yeah, it's 0. Yes. Can you tell me why? Yeah, it's right. It's 0. Mm, uh, actually, the Grundy number is like because yeah, of uh, two even numbers. Yeah, you're telling me something. Yeah, it's because there's no way for player one to win with even number. Uh, not really. Like for if you have six, I think. Mm, no, not this one. Yeah, I understand your ideas, but yeah, it's right for the four. The Grundy value is zeros because uh, because Ramazan already told this about you guys about this. We need to calculate all the possible position, next position. So if a player had four stone, right, then he can take one or two or three, but he cannot take four stones. So the next possible position for the games is only three, two, and one. Yeah, 3, 2, 3, 1, 2. Yeah, 3, 2, 3, 1, 2, right. And Grundy of four, yeah, Grundy of four is 3, 2, 1 is equal to zero because Grundy of four. Uh, Let me delete this. Okay, uh, Grundy of four, Grundy of four is equal to mace. We are using the theorem we already proved from the theorem proved by Ramazan. So here we have 1, 2, and 3 equal to zero, right? The smallest integers here is zero. It's not in the set, but like the smallest integer you can five. So, but yeah, but uh, what can I talk? So let's try to calculate the Grundy for five. Grundy value for five. Grundy number. Is the Grundy number for four stone two? No, it should be zero because you we define the value for Grundy. No, and I type here. So let me type in the chat. So uh, Grundy values, the Grundy values for the neck. No, it's not. Why the Grundy is zero is not two because if a player has four stone, he can take one or two or three, and the next position of the game is can be 3, 2, 1, right? And so the Grundy of four is Grundy of four. We need to calculate the makes of all the possible position. So all possible position is 3 and 2 and 1. That's the formula. So that's because we have 3, 2, 1 is equal to zero. Because that's the definition of the Grundy numbers when we yeah, what you are asking here. Yeah, okay. Yes, okay. So because it's you can see here that that's the max value for this is zero, and I assume that Ramazan already told you how to calculate this. And I think I let me try to calculate the Grundy value for five. Uh, yes, let's try to calculate for five. What the result will be? No, it's not. It won't be. It won't be. It won't be zero. Why? Uh, yeah. Actually, I should tell you like this. It should be like this. It should be like uh, G and uh Actually, the formula for this, it should be here. I made a small mistake. So uh, thief n minus one. We are calculating only base case. Yes, z minus two, because you need to use recursive to calculate this, and z n minus three. Yeah, we are calculating for the base case. We're calculating for 1, 2, and 3, and 4. So if we are thinking about this, so Grundy is like for 4 is here we have 3 and 2 and 1. But this problem it's not a formula for all, because what we are doing here is like we are calculating this for because the problem is we can only take 1, 2, or 3 stone, not all. So if we have 5 here, so let's say if we have 5 here, we have 5 here, so yeah, so it should be 2, 3, and 4, right? No, 4, 3, and 2. Yeah, it should be 4, 3, and 2 here. And the value of Grundy 5, it should be 1. G5, it should be 1. And G6, it should be 2. Yeah, because you can calculate the mass from z n minus 1, z n minus 2, and z n minus 3. Base case already. Yeah. Because let me. Maybe I need to tell you like again about the mates if you want, but I think it will be could take a lot of times here, right? Mm. So let's well, is there uh well, let me ask you. Well, I think we need to think, check again, because you guys are understanding the max function is wrong. So what is the max of well, let's say 1, 2, and 3? I made a mistake before for the definition before, so I just want to ask you guys, what do you think the solution here, the max for 1, 2, and 3? If the max is I mean minimum is excluded. Minimum excluded, yeah. Right, yeah, it's right. So what would be the results here? If 0, 1, 2, and 6. Yeah, the results here. Yeah, I just want to tell you how not cut to 10, but I mean uh I want you guys to understand it, how to calculate the values. So here is 1, 5. Because 1 is the smallest non-negative number not present in the set. The smallest non-negative number not present in the set. Mm, and you get it? Do you guys get it? Uh, I mean, I'm sharing the ideas first, not the code, because if you don't understand it, no need to. equals. So let's say if we have base of let's say 0, 1, 4. Yeah. What will be the results here? Yeah, yeah, it's okay. I mean, I don't think it's live, a lecture live. I think it's live. We are having a talk at a cafe, so we discuss something we know about it. Yeah, I got you. Yeah, yeah. So what the makes from 0, 1, 4, and 7? What the smaller non-negative numbers not present in the set is 1. Yeah, that's right, 2. Yeah. Right, so you got the idea how to calculate the Grundy values. You need to calculate the mates first. You need to know how to calculate mates, and then you know how to calculate uh, Grundy's Grandier values. Yeah, so I think you guys already got it. So why? Yeah, just 1 minute, please. Um, what is worse with here is like I forget it. Yeah, so yeah, that we should return with the Grandies. Grandies. So yeah, so 4 is equal to what? The smaller it is, right? 2, right? No, it's equal to mix. And it's equal to 0, right? Uh, and Z5 is equal to mix 2, 3, 4, and equal to 1. Yeah, so similarly, you can do for Z6. Z6 is 2, Z7 is 3, and so on. So why we are calculating the Grundy numbers? Because we need this for calculating the result of the game to decide if the game is the first player can win or not. So let me write the tasks in the chat for you guys. So let's and 5 of stones. You can take 1, 2, or 3 30 stone from any 5. My if the first my good player win. Yeah, so we already know the Sprague theorem. We need to calculate the Grundy value for 8 bytes. We need to solve all of that, and we get the final solution. So let's code something here. So um, so we need to process. Of course, here I will explain it to you a little bit. We need to define the sum short is equal to 0 first. And for each case, okay, we have. And what we doing here? We are doing here. So what we are doing here is I will explain this slide later. And we need to return some source. If yeah, so for the main function. Mm, yes, this is yes, and size here equal to 0. This is plus this and yeah, yes, and so let's make the first case when we are uh, yes. No. Sorry. Here should be yeah, one, two, three. Yeah. 1, 2, 3. What does this mean? Like we have only one test case, right? We have two pies. I'm testing for only two pies. We have 4 stone on the first pie and 1 stone on the second pie. And the first player will win. Why? Because we already told but before that we can take 3 stone from the first pie, and then it will be definitely a win for the first player. Because why here we have here this one, because we can see that well we're not gonna prove it, but you can check it here. You can see it here, right? Uh, I can share the costs. I mean, yeah, I should share the costs. Yes. If anybody needs it. So why I I write like this? I write because we can see it here. What we are calculating here. We are trying to calculating or uh, the Grundy values. Yeah. We are trying to calculate the Grundy values. And it's coincide with this. Let's check. These ones. This 0 is equal to zeros, right? This one is equal to what? Z1 equal to 1 and so on. Z5, we are Z5. Z5, we already calculated it. Z5 equal to Z5 equal to 1. And Z6 equal to 2. It's the same as x power 4, right? If 5 is 4, and we get 1. Divided divide 4, then we will get 1. Six, not divide, but divisor 0, right? I'm, why my English is so bad. It's 2, right? It's the same with Grundy values. It's the same with Grundy values here. So what we are doing here, so we're calculating Grundy value for 8 bytes. We input 8 bytes here, we calculate the Grundy values, and we store all of this to get the solution. So if the final result is positive, then the first player can win. If not, then the second player will win. But yeah, it's the results, but the strategy is that you need to maintain that the sort of spice some, so yeah, a new message. Yeah, using Bitcoin. Yeah, yeah, right. And why we are doing that? Because you apply the theorem Ramazan already proved that we need to store all of the Grundy values of big pies. Uh, and we get the results. So yeah, so let's check with the more test case if you want to test with, let's say, uh, with test case I can get, well, let's say if we have mm, 1, 3, 4, 4, 4. Oh, second player will win. Yeah, second player will win. Yeah, because the sword here is if we have force of 4 and so 4, the result it should be yeah, it should be negative. Yeah, yeah. Yeah, yeah, I think so. Yeah. So that the idea I want to share with you guys at this seminar. So what we did. So we are as no, I mean we already did one simple name game. We already know the name game when we can take any number of stone. And the second we play a game where we can only take one or two or three from the pipe. And the important thing you need to know about this is that you need to know how to calculate the Grundy values. You need to know what make is, what the Grundy value is, and why this work. I already told you that because the Sprague Grand theorems. That's why it's important for you guys to know that. And Ramazan already proved it at the beginning of their seminars. Uh, yeah. If anybody have a question, please tell me. Yes. Yeah. uh, okay. Ramazan, are you still here? So I think it should be live. Yeah. Sorry. Yeah, yeah, of course. Yeah, 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 yeah. I think it's okay. It's enough because uh, mm, I mean, the reason why I introduced you guys this problem because I think it could be I will include a difficult version of this problem in the contest. And it's really interesting because I think in the final year in MIPT you guys will have a course in game theory, and this could be useful for you guys. Uh, it's like it's really interesting research fields, game theory. So I mean, yeah, and I will include the exercise about this one. So yeah, I finished. I'm done. Okay.